Now let's take a look at the last two sections in Chapter 4. Section 4.5 is the real zeros of polynomial functions, 4.6 complex zeros, and the fundamental theorem of algebra. These sections are really full of a lot of definitions and theorems that you need to make sure that you know and understand. So before we work a problem, we need to go back to the book. Okay, and this section starts off by pointing out that, we've worked with polynomial functions before. We know how to deal with lines. We know how to deal with quadratics. We know how to factor some polynomial functions if they factor pretty simply. But what this section points out is there are lots of polynomial functions that don't behave as nicely as the ones we've seen in previous sections. So what do we do when that happens? Okay. So the first sentence on page 221 is really loaded, and you need to make sure you think through every piece of it because it really gives you about 5 different ways to say the same thing. Okay, so recall that if r is a real zero of a polynomial function, then that means that f of r is 0, r is an x-intercept of the graph of f, x minus r is a factor of f, and r is a solution to the equation f of x equals 0. So they can present it in any of those ways, and it all is getting back at the same idea, presented either in terms of the function, in terms of solving an equation equal to 0, in terms of a graph, but you've got to be able to interpret what they're saying. Okay, so when we have a polynomial that doesn't want to behave nicely, and meaning that it's not a little one that we can factor like we've been doing right along, we're going to use some techniques of division. So the first thing they do is they remind you, hey, long division, you know how to do it. Whenever you do division, you get a quotient, you get a remainder. And so we can rewrite it once we do the divisor into the dividend. We can rewrite the dividend as the quotient times the divisor plus the remainder, and that will be equal to the original dividend that we started with. Okay? I don't know why I've got a little circle going on today, but we got a circle. All right, so what we're going to do with this is we're going to go over and we're going to play with the remainder theorem. What the remainder theorem tells us is suppose you have this function and I want you to divide it by something that looks like x minus c. Then the remainder that you get when you do that division is exactly the same thing that you would have gotten if you had plugged in c to the original equation and figured out what that value was. Okay, so the thing is, whenever you want to use the remainder theorem, you're wanting to divide a function by a little linear factor, okay? But instead of literally doing the division, what you're going to do is you're going to plug c into the function and get the function value, and then this theorem says, hey, guess what? That function value is the remainder. Okay? Now you're going to put that together with the factor theorem. Okay, the factor theorem is this one. Okay, if f is a polynomial function, then we say x minus c is a factor of f of x if and only if f of c is 0. And so that if and only if statement in math means it goes both ways. It's really two different statements. So if f of c is 0, then that means that x minus c is a factor of f. Or if I tell you that x minus c is a factor of f, then you know f of c is 0. So either way. So let's go back to the PowerPoint and see if this will stop doing the little circles. There we go. All right. So this is a typical problem. So use the remainder theorem to find the remainder when f of x is divided by x minus c. So here, this is f of x, and then you're going to divide it by x minus 2. So that's the x minus c. So now we could literally take x minus 2, divide it into 4x to the 4th minus 15x squared minus 4. But if it specifically says to you to do it by the remainder theorem, then what they're saying is they want you to plug c into the function. Okay, so we want to do f of c. C here is 2. Watch your signs. It's x minus c. So x minus 2, 2 is c. So you're literally going to plug c into the function and see what happens. So, 4 times 2 to the 4th minus 15 times 2 squared minus 4. Okay, can you crunch that? That's 4 times 2 times 2 is 4 times 2 is 8 times 2 is 16. Minus 15 times 4 minus 4. So 4 times 16 minus 15 times 4 minus 4 is 0. So use the remainder theorem to find the remainder when f of x is divided by x minus c. The remainder is 0. F of 2 is 0. 0 is the remainder. Now use the factor theorem to determine whether x minus c is a factor. Well, the factor theorem says that if I have this, then I know that x minus 2 is a factor. I'm going to just say of f of x rather than writing that out. So f of 2 is 0, so I know that x minus 2 is a factor of f of x. Okay. So it's really just a matter of understanding those theorems. Okay, let's go back to the book again. Okay, so we were here. All right, this is them working an example. Okay, so the number of real zeros. If you have a polynomial function, it cannot have more real zeros than its degree. So that's really helpful, especially in just a minute when we're going to start just looking for zeros. It's not going to be something that factors the way we're used to, and we have to find all of the zeros. So it's really cool if we can look at the degree and we can say, oh yeah, the degree is 5 or the degree is 4. So you know how many answers you're looking for. Okay. And then we're going to play with this rational zero theorem, okay? Now, it looks really weird, but it's not that bad. What it really does is it gives you a way to take a polynomial function and figure out what the possible rational zeros are. Okay? And what I'm going to do is I'm going to actually take this theorem and I'm going to walk you through it in an example so that you can hopefully understand it. But notice there'll be two types of problems that deal with this. Sometimes I'll just say, hey, use that theorem and write for me all the possible rational zeros. Other times they will give you a problem like this down at the bottom, and you'll have to use that rational zero theorem to get these possible zeros, and then hope and pray you can find which one of them is actually going to work. Okay, so let me just show you how this works. Okay, all right, so we're here. Okay, so suppose I say, here's some polynomials, and I want you to tell me what's the maximum number of real zeros that they can have. I'm not even bothering to find them here. Just tell me how many they're going to have. So what you do is you look, find the degree. So the degree of this one is 4. So if I say to you, what's the maximum number of real zeros? You say 4. For the other one, the degree is the highest power on x. That's 3. So what's the maximum number of real zeros? 3. Okay. All right. So now this is just, can you use the rational zero theorem to find these possible zeros? Do you remember way back in the appendix? So like when we were talking about numbers, you know, we talked about, we had rational numbers and we had irrational numbers, and together they make up the real numbers. And then we started talking about imaginary numbers, and the real and the imaginary make up our complex number system. Okay, so what the rational zero theorem does is it tells you that if you have a polynomial function and it's going to have rational zeros, it's going to give you a list of the possible numbers they could be. Okay, so now notice, it's giving you these. Okay, it does not give you the irrational real numbers. It doesn't give you the imaginary numbers. It's just if there is a possible rational zero, it will be in this list, and then you can check it and see which ones are actually zeros. Okay, so the way the rational zero theorem works is you make these little baby fractions. And the first thing you do is you make a list of the factors of the constant, and they call the constant p. And so you just write down every number you can think of, pairs of numbers that multiply together to give you 2. So luckily we've got 1 and 2. Do not forget -1 and -2. Okay, so really, there's 4 numbers there. Then Q, I'm going to change colors, sorry. Q is the leading coefficient. So the number in front of the x to the highest power. Do the same thing. Give me all the possible pairs of numbers you can think of that multiply together to give you 6. Okay? So 1 and 6, 2 and 3. And yes, I like them in order. And again, do not forget, if you've got 1 and 6, you've also got -1 and -6. +2 and +3, -2 and -3. Okay. So just all the factors. So then make a list of all the fractions you can make putting the numbers from P over Q. Okay, these are going to be your possible rational zeros. Okay, your possible rational x-intercepts of the graph. Okay. So let's see. Take all of the red numbers over all of the blue numbers, whichever way makes sense to you. Let's see. I'm going to do 1 over 1. Then I'm going to go 2 over 1. Then I'm going to do 1 over 2. 2 over 2 is 1. I already wrote that. Then I'm going to do 1 over 3. 2 over 3. And then 1 over 6. 2 over 6 is 1 over 3. I already wrote that. Did I get them all? Don't forget the pluses or minuses. Okay, so 1, 2, 3, 4, 5, 6, 12 possible rational zeros. So if this particular function, when you graph it, if it's going to have any rational zeros, they're going to be one of those 12 numbers. Okay? All right, let's do another one just to make sure you've got this pattern down. So if you want to know the possible rational zeros, again, the factors of the P, happens to be 6 again here. Okay, so ±1, ±2, ±3, ±6. Then the Q is the factor of the leading coefficient. So for 4, we've got 1 and 4, 2 and 2. And again, that whole plus or minus thing. Here thinking a +1, a -4, a -1, a +4, but still ends up being the same kind of list. Okay? All right, and then the P's over Q's, the possible rational zeros. Let's see. So 1, 2, 3, 6. 1/2. 2 over 2 is 1. 3 over 2. 6 over 2 is 3. I already wrote that. 1/4. 2 over 4 is 1/2. 3/4. And then 6/4 is 3/2. I already wrote that. Okay, so plus or minus, plus or minus, plus or minus. My commas in there. And if you wanted to do it as a roster, technically you'd have it in curly brackets, like so. Okay, so again, if there are going to be rational zeros of this polynomial right here, it has to be one of these numbers. Okay, any rational zeros that this function has have to be in this list. All right, so number 5, page 5. So use the rational zero theorem to find all of the real zeros. Then use those zeros to factor f. Okay, so look here. All right, so if you looked at this, could you factor it? You might could. Maybe you know some factoring by grouping. Maybe you'd recognize it. But they said use a rational zeros theorem. So let's see how it works with this. All right, so if this thing is going to have a rational zero, we know how to find them. The P's are going to be the factors of 30. Okay, so can you write those down? Let's see. I'm going to put a plus or minus out front. I'm not going to forget it. And then, let's see, the factors of 30. 1 and 30, 2 and 15, 3 and 10, 5 and 6. Okay, so is that all of them? 10, 15, and 30. Is that right? Right. The Q's going to be the factors of 3. So plus or minus 1, plus or minus 3. And then if this is going to have rational zeros, we can figure out what they are. Let's see. And again, I'm putting the plus or minus out front because I just don't want to write it every time. All right, so best way you can, make sure you pair up all these numbers. So first I'm going to take all the p's and put them over 1. So it'll give me 1, 2, 3, 5, 6, 10, 15, and 30. And then I need to take all those numbers and put them over 3. So 1 over 3, 2 over 3, 3 over 3 is 1, 5 over 3, 6 over 3 is 2, 10 over 3, 15 over 3 is 5, 30 over 3 is 10. Okay, that's it. Okay. So now what do we do with this? So if this thing has a rational zero, it's in this list. If it's a 0, then that means if I divide that number into the function, I should get a remainder of 0. And I've got my remainder theorem that we could use, and I also have synthetic division. I'm going with synthetic division because I think it's faster. But what I'm after is if I take 1 and divide it into f of x, okay, do I get a remainder of 0? Okay, and I'm going to do it by synthetic division. Okay, so remember we pull off the coefficients: 3, 6, negative 15, negative 30. What I'm after is a remainder of 0. If I get a remainder of 0, then I know x minus 1 is a factor. Okay, so here we go. Bring down the 3. Multiply. Add the column. 1 times 9 is 9. Add the column. Negative 15 and 9 is 6. Multiply again. 1 times 6 is 6. Negative 30 and 6 is not 0. Okay, that didn't work. Okay, let's try another. Let's go negative 1. See if I can get it to fit here. Into 3, 6, negative 15, negative 30. All right, so that's negative 3. 6 minus 3 is 3. Negative 1 times 3 is negative 3. Negative 15 and negative 3 is negative 18. Negative 1 times negative 18 is 18. That's not 0 either. Okay, so you see what I'm doing? I'm just trying numbers. I'm trying to find one that works. There is no, well, there are different things that we can look at, but honestly, I'm going after the numbers that are easiest to do the division with. I'm going to go to 2. Okay, so I'm going to do 2 into 3, 6, negative 15, negative 30. Okay, so to 6, 12, 24, 9, 18. That's not 0. All right, negative 2. Okay. This can go on for hours. I'm teasing, no. But as far, I mean, it is just a process. You're very quick at synthetic division. You're just trying to find one that gives you 0. Okay, so negative 2 times 3 is negative 6. 6 and negative 6 is 0. Negative 2 times 0 is 0. Negative 15 plus 0 is negative 15. Negative 2 times negative 15 is 30. There we go. Okay. So, okay, think for a second. This says to us that x plus 2 is a factor of the original function. Okay? Now, if this were a bigger, now this is only degree 3, right? So if we divided something that was degree 3 by something that was degree 1, that means that this quotient down here is a quadratic, right? So what, 3x squared plus 0x minus 15. Okay. So if we wanted to write f of x in factored form, so far what we've got is we've got x plus 2 times the quotient 3x squared minus 15. Now, luckily, we know how to deal with quadratics. If this had been something of a higher degree and we found that -2 was a 0, we would have to check -2 again because we don't know the multiplicity. Perhaps -2 would have worked more than once. But again, since this original problem was degree 3, that means the first quotient that I get when it works is a quadratic, and I can deal with quadratics in other ways. Okay, so see there's a common factor of a 3 that I could pull out. So if I pull that 3 out of there and put it in the very front, what is that, x squared minus 5? That's completely factored over the real numbers. Okay? But notice how it also wants us to find all the zeros. Okay, so now what we've got is we found the -2. Okay, but that's not all of them. This thing is degree 3. So what we've done is we've found the only rational one that we've got so far. Okay, the others are going to come from the quadratic. Okay, so from the x plus 2, we got -2. From the x squared minus 5, what happens when you set it equal to 0? You get x squared equals 5. X equals plus or minus the root of 5. Okay, so if I had to find all of the zeros of this particular function, it's -2, positive root of 5, and negative root of 5. Those are my zeros. All right, I'm going to try another one. Notice how this is presented differently. This one says, hey, solve this thing over the real number system. Okay, so it's not presented as like f of x equals find the factors. It's presented like this, find the solutions to this equation. What's the same idea? Think about this as being your function f of x. Okay, and think about that sentence that was on the top of the second page in the section. Okay, if we want to find the solutions to the equation, we want to find the factors that divide in with a remainder of 0. We want to find the x-intercepts. We want to find the places where f of c is 0. So all those different things floating around. Again, we're going to start the way with the rational zero theorem because that's about all we can do. Okay, so rational zero theorem, factors of 5, plus or minus 1, plus or minus 5. Factors of 2, plus or minus 1, plus or minus 2. So my P over Q's, 1, 5, 1/2, and 1/5. And 1/2 and 5/2. I just said that second one, put that one backwards. And 5/2. Is that right? So 1, 5, 1/2, 5/2, plus or minus on all of them. Okay, so, ready? 1 into 2, -3, -3, -5. See what happens. Bring down the 2. 1 times 2 is 2. -3 plus 2 is -1. 1 times -1 is -1. -3 plus -1 is -4. That doesn't work. Okay? So try again. Try -1. See what happens. Okay? Now, again, I want you to practice. Okay, so like stop the tape for a second and practice. See if you can find the one where it works. Okay? I'll tell you, I tried -1, +1, +5, -5, +1/2, -1/2, and got all the way over to 5/2 before I found one that worked. Just unfortunate the order I chose. Okay. All right. 5/2. And again, like I said, you're just going to test them until you find one that works. Okay, so I hope you check the division on the others. Make sure I didn't make a mistake. Pretty sure I didn't, but let's see. So 5/2 does work though. Okay. So bring down the 2. 5/2 times 2 is 5. -3 plus 5 is 2. 5/2 times 2 is 5. -3 plus 5 is 2. 5/2 times 2 is 5. Remainder 0. Hallelujah. Okay. All right, so we're supposed to solve this thing over the real number system. So right now what I've got is I've got 1, 0. Okay, so if I were going to write this, I have x minus 5 halves times, again, the quotient. We started with an x to the third. We divided it by an x to the first. So because of that, we know that our quotient here is quadratic. So we stop as soon as we can get to a quadratic because we have other ways to deal with that. We know how to factor, complete the square, quadratic formula. No need to keep with the synthetic division stuff. Okay. See the 2 common in the trinomial? I'd pull that 2 out. Okay. Now our question is to find the zeros, but just to kind of show you a couple of things together. When you do synthetic division, you've got the 5 halves. And then when you factored out the quadratic, you had this factor of a 2. If you were told to leave this in completely factored form, it's kind of bad to leave it written as it is right this second. If you were told to write this in completely factored form, I'd take that 2 and distribute it into the little binomial so that you have 2x minus 5 times x squared plus x plus 1 if you were told to factor it. Okay. Now again, we're just after the solutions, the places where this equals 0. We've already got the 1, the x equals negative 5 halves from the first binomial. Whether the 2's in it or not, we get the same thing. Okay, so if we're going to have any others, it's going to come from x squared plus x plus 1 equals 0. So you may factor it, complete the square or quadratic formula. Quadratic formula. So negative 1 plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So negative 1 plus or minus the square root of negative 3. Okay, that's not real. So this is where you pay close attention to the directions, because in this particular section, we're only going after real answers. So we stop, we don't give this answer. In the very next section, it's going to say solve it over the complex numbers, and then we would just pull out the negative 1 with the I. We'd write it as a pretty complex number, and we'd include it as a 0. So pay attention to your directions. If your directions say they only want real numbers, then the only thing that's acceptable is the negative 5 halves. Or excuse me, positive 5 halves. Where did I get negative 5 halves from? Positive 5 halves. Okay. In the next section, when they change the directions and they say complex, then we would include these as well. All right. Want to try another? I'm just trying to do several examples of these. Feel free to stop and work it yourself and then come back. All right. So let's see. So I'm supposed to solve this. This one is degree 4. Okay, so I'm already kind of getting into my head to start with that whenever I find a 0, my quotient that I'm going to have from that first division is going to be cubic. It's going to be to the 3rd power. So it's not going to be a quadratic where I can just quit with my division and go on and do it the way I've always done it. I'm going to have to keep on going until I can get it down to the term so that I only have the quadratic. Okay? All right, so let's see. Let's start with the p's over q's, and I'm going to put them way up here so I'll make sure I've got plenty of space. Factors of p are the factors of 9. So plus or minus 1, 3, and 9. Factors of q, hey, 1. Leading coefficient's a 1, so that works. So my possible rational zeros, if this thing is going to have real zeros, rational zeros, it's going to either be positive 1, negative 1, positive 3, negative 3, positive 9, or negative 9. Okay. And then hopefully by the time we find the rational zeros, that'll break it down far enough that we can find any remaining irrational ones or complex answers. Okay, so I'm going to start with 1. Into 1, negative 2, 10, negative 18, 9. Bring down my 1. 1 times 1 is 1. Negative 2 and 1 is negative 1. 1 times negative 1 is negative 1. Okay. 10 minus 1 is 9. 1 times 9 is 9. Negative 18 and 9 is negative 9. 1 times negative 9 is negative. Okay, 0. Woo, yay. Okay, so what that says to me is I know that 1 is a real 0. So we're like, yes. But it won't do me any good to stop right here and say x to the third minus 1 minus x squared plus 9x minus 9, because I don't know what to do with that. So I'm not even going to stop yet. Okay? I'm not going to stop using the rational zero theorem until I am sure I've got it down to a quadratic. Okay? So now your choices go on to negative 1, 3, negative 3, 9, negative 9, or remember about multiplicity, that it is possible that 1 could have a multiplicity of 2 or 3 or 4. Okay, maybe 1 is going to work again. Okay, so I would go ahead and check it one more time. It just makes everything easier. Check and see if it works. Okay, so now you're going to divide into the dividend 1, negative 1, 9, negative 9. Okay, see what happens. 1 times 1 is 1, 0, 1. Oh, no, 1 times 0 is 0. 9 plus 0 is 9. 1 times 9 is 9. Negative 9 and 9 is 0. Okay. All right. Now, this quotient is quadratic. Now I'm going to stop. All right, so what have I got so far? I've got the factor x minus 1 from here. I got another x minus 1 from here, so I'm going to write it as x minus 1 squared. And then x squared plus 0x plus 9. So x minus 1 quantity squared, x squared plus 9. If it's said to factor it completely, that's factored completely. X squared plus 9 is a sum of squares. It doesn't factor anymore. So if it was asking for the totally factored form, that would be it. Okay, so we know we get the 1 from the first factor. From the second factor, if we set x squared plus 9 equal to 0, we get x squared equals negative 9. And we get x equals plus or minus, what is that, 3i? Well, in this section, it only wants the real answers. The 3i, they're not real, so they don't count for this section. So for this section, if it wants the answer is 1. Once we go into the next section, we'll include the 3i and the negative 3i. But for right now, for the real numbers, okay, we don't want the ones with the little i's on them. Okay, so intermediate value theorem. That's a go back to the book for a second thing. Okay. So suppose, we've been pretty lucky so far. The ones that we've done, we've been able to get the 0 without too much trouble. But there is another theorem that can help us. It's called the intermediate value theorem. And what it says to us, if you think back to those problems where you were having to answer where f of x is greater than 0, or where g of x is less than or equal to 0, where you were looking at the graph and you were trying to figure out where it was above or below the x-axis. The intermediate value theorem builds on that idea. What it says to you is if you can find two different x values, where one of the x values, when you plug it into the function, you get a positive answer, and the other one, when you plug it in, you get a negative answer, you're guaranteed that the graph has to cross the x-axis in between those two x values. Does that make sense? Okay. So if I have, where's the actual down here? So if I've got a polynomial function, and I've got two x values, a and b, and I know that when I plug a and b into my function, I get opposite signs on my y values. So one of them gives me a positive answer, one of them gives me a negative answer. Well, the only way it can happen is if the 2 points have to be connected, right? So if they're connected, I got to go across the x-axis. Okay, so the intermediate value theorem guarantees us if we can find these x's that have y values of different sign, we're guaranteed that there must be an x-intercept or a zero, a real zero, in between those two x values. Okay, so the way it'll work here is it'll say use the intermediate value theorem to show this. So what you do is you want to figure out what the function value is when you plug in -3 and what the function value is when you plug in -2. Okay, and you're going to hope that one's positive and one's negative. Now you can use synthetic division if you want to get the function value, or you can do good old number crunching, whichever one works for you. Okay, so 3 times -3 quantity cubed. -3 quantity cubed times 3 is -81, plus 30 plus 9. That's what, -42. Plug in -2. So 3 times -2 quantity cubed minus 10 times -2 plus 9. That's -24 plus 20 plus 9. That's 5. Okay, so think about it. So when x is -2, you got a y value that's up here. When x is -3, you get a y value that's way down here. And so if it's a polynomial function, it's continuous, so these points have to be connected. And if they're connected, it's got to go across the x-axis. So you're guaranteed that somewhere in between those numbers, in between those two x values of -2 and -3, there is an x-intercept. Okay? So to write it pretty, I just say since f of -3 is less than 0 and f of -2 is bigger than 0. And I'm purposely writing it that way so that it connects back to those other problems we were doing. Okay, since one is negative and one is positive, then by the intermediate value theorem, we know that there must be a 0, or an x-intercept if you'd rather, between x equals -3 and x equals -2. So it's a way to check. So when you have one of those really, really, really long lists, you could check different values just to see, to maybe help pin it down. It just depends on how long the list is and how much time you want to take in trying to pin it down. Okay. All right. So this is 4.6. So let's look at the book again. Okay. The main thing that 4.6 gives us is it adds in the complex zeros. Okay, so now instead of saying, hey, solve this thing over the real numbers, it's going to say, hey, solve it over the complex numbers. So it just means we won't leave out those complex answers anymore. We'll continue and we'll get them. One really cool thing that you need to keep in mind is this conjugate pairs theorem. And what's wonderful is that when you have this polynomial function and you want to try to find the zeros, you know you're going to find at least one. And if you happen to find one complex number, you are guaranteed that its conjugate will also be a 0. Okay, so they come in pairs. You won't get 3i unless you get -3i. You won't get 5 minus 7i unless you get 5 plus 7i. So if they tell you one, you know what the other one is. Okay, so that is really the only difference. Again, here's the polynomial function of odd degree with real coefficients. Oh, look at that one. So we've got this, and then they say, hey, wait a minute. A polynomial function of odd degree with real coefficients has at least one real 0. So there they go back with that real part. Does that make sense? If you have a function with an odd degree, Does it make sense that it absolutely must cross the x-axis? Okay, remember how we said polynomial functions start and end in different places? They either start high and end low, or start low and end high. So it's going to have to cross the x-axis. So if the function is of odd degree, we know it's going to have at least one real zero. If it's even degree, it might not have any real zeros at all. They might all be up here in this imaginary category. Okay, but if it's odd, we know at least one of them will be real. All right, so then they go into the problems. So we're ready to go back to the notes. Okay, so suppose I tell you that these are the real zeros of my function. Could you please find the rest of them? Is basically what they're after. Okay, now do watch how they write this. Do you see how this is? That's a complex number. They've written three numbers. They've written 1, 2, and then the 2 plus I is a complex number. Okay, so if this thing is degree 4, across the complex number system, I know I'm supposed to have 4 zeros. Okay, I've got 1, I've got 2, I got 2 plus I. You say to yourself, okay, I also have to have 2 minus I. So when it says find the remaining zeros of f, 2 minus I is your remaining zero. Okay. All right, for the second one, again, degree 4, I'm supposed to have 3 answers. Again, watch how they type this. This is 2 minus I, and that's minus I. So those are the two numbers that they're giving you. And sometimes when the way they type this, it just looks weird. Okay, so you say to yourself, if 2 minus I is a 0, 2 plus I must also be a 0. If negative I is a 0, positive I is a 0. So 1, 2, 3, 4. 4 complex zeros. Okay. All right. Oops. Go here. Okay, so form a polynomial function with real coefficients having given degree and zeros. Answers will vary depending on the choice of leading coefficient. Okay, so we want to find the complex zeros, and we want to write this thing in completely factored form. Okay, what you want to do first? Oh, wait, that's not the right screen. Sorry, I turned the screen in there. So form a polynomial function with real coefficients having a given degree and zeros. Answers will vary depending upon leading coefficient. Okay, so let's think. If I tell you that 1 is a 0, you know that it's an x-intercept. You know that it comes from the factor, what, x minus 1? So I'm going to say f of x equals. All right, so if 1 is a 0, it comes from the factor x minus 1. If they then say that it's got multiplicity 3, that tells me I can put a 3 on my factor because I get 1 as an answer 3 times. Okay, but then 1 plus I is an answer. Okay, it's a 0. So now be very careful how you put that back in the factor. We said x minus the 0, 1. So now we're going to go x minus the 0, 1 plus I. And be careful with those double parentheses. Okay. Now, think about it. I got 1 3 times, and then I got the 1 plus I. That's 4, and I'm supposed to have degree 5. So I'm missing the other conjugate. I'm missing the 1 minus I. Okay. So put it in the factor, x minus the 0. All right, so see this part? This says we can't leave it this way. Say real coefficients, that means they do not want it left with those i's in there. So we're going to have to multiply this out. I'm perfectly fine with leaving the x minus 1 to the third. Sometimes the book will make you multiply it all the way out, expand it completely. For me, if I can get these two together, then it's it's a quotient, it's a product of polynomials, and then I'm cool with it. But notice that if it strictly says form a polynomial function, then you really have to take it all the way in some of the problems. Okay, so all right, let's get rid of all these double parentheses. This is x minus 1 minus I times x minus 1 plus I. And I would definitely do that in 2 steps or you will mess up those signs. Okay. So I'm going to multiply that out. I'm going to take the x times all 3 pieces in the second trinomial. I'll get x squared minus x plus xi. Then I'm going to take the minus 1 and I'm going to go times all 3 pieces. So minus x plus 1 minus I. And then I'm going to take the minus I times all 3 pieces minus xi plus I minus I squared. Okay. So let's see, this and this add to 0. This and this add to 0. Do you remember the minus I squared? Do you remember that I squared is negative 1? So this is actually the same thing as plus 1 out there on the end. Okay. So x minus 1 quantity cubed, x squared minus 2x's plus 2. That's without any imaginary numbers. Okay, again, like I said, you could continue from this and multiply it out, and I know you can do that, but for us, for now, I'm going to stop here because if anything is going to give you trouble, it's going to be that part right there that we just did with the conjugates. Again, so be real careful. Okay. All right, how about here? Okay. Now, if they had told us, like, here's this function, all right, it's to the 4th degree, and they gave us a 0. So if we had been lucky enough that it had been like 5 or 10, we could have done synthetic division and we would have gotten a remainder of 0 and it would have broken it down and it would have made it nice and simple for us. But notice how they kindly gave us a 0 that is a complex number. Okay. So if 1 plus 3i is a 0, I know that 1 minus 3i is also a 0. If I know that the factor that contains the 1 plus 3i, that came from what? X minus 1 plus 3i, and x minus 1 minus 3i. Now, I don't know about doing division with those complex numbers, okay? But I do know that if both of those things are factors, if I multiply them together, their product will also be a factor. And I know from what I just did in that other problem that if I multiply these two things together, it's probably going to be a lot prettier than what this is. Okay, so because they tell me that 1 plus 3i is a 0, I know 1 minus 3i is a 0. I know that they will divide in with a remainder of 0. Their product will divide in with a remainder of 0. Okay, so I'm going to fix this before I do any division. Let's see. I'm going to do exactly like I did before. Distribute the minus sign and get rid of one of those parentheses. And the same thing here. Okay, and then I'm going to multiply it out. Let's see. So x squared minus x plus 3xi minus x plus 1 minus 3i minus 3xi plus 3i minus 9i squared, which I know is negative 9 times negative 1, which is plus 9. So this and this add to 0. This and this add to 0. X squared minus 2x plus 10. Okay, so what I know is that x squared minus 2x plus 10 is a factor of f of x. If it's a factor, then it should divide in with a remainder of 0. Okay. Now, I have to do this by long division, okay? So, let's see. I'm going to divide x squared minus 2x plus 10 into x to the fourth minus 7x to the third plus 14x squared minus 38x minus 60. Now, I mean, it would have been nice if I could have done synthetic division, but I can't with this, but at least I'm guaranteed that the remainder is supposed to be 0, so this should do fairly easy. Remember, go first term into first term. X squared into x to the fourth goes x squared times. Multiply. X squared times x squared is x to the fourth. X squared times minus 2x is minus 2x to the third. X squared times positive 10 is plus 10x squared. Subtract. Change the signs. Okay. Those add to 0. Minus 5x to the third minus, that's a plus. From here, that should be plus 4x squared, and then bring down the minus 38x. Okay. X squared into minus 5x to the third goes minus 5x times. What do you multiply x squared by to get negative 5x to the third? Negative 5x. Okay, multiply. You get negative 5x to the third plus 10x squared minus 50x. Subtract. Change the signs. Those add to 0. Negative 6x squared plus 12x minus 60. X squared goes into negative 6x negative 6 times, and if we're lucky, it should go beautifully. Negative 6 times x squared is negative 6x squared. Negative 6 times negative 2x is plus 12x. Negative 6 times positive 10 is negative 60. Subtract, change the signs. That adds to 0. Okay. So where does that leave us? All right, so what we've got is we know that f of x is x squared minus 2x plus 10 times x squared minus 5x minus 6. We got this from the two complex zeros, so we already have those two zeros. Okay. So what do we do with this? It's quadratic. Factor complete the square quadratic formula. Luckily, that little baby factors x minus 6, x plus 1. So set this one equal to 0 and you get 6. Set this one equal to 0 and you get negative 1. So if it says find the remaining zeros, 1 minus 3i, 6, and negative 1. So that's 3. The one they gave us makes 4. The degree on this thing was 4. That's all of them. Okay. All right, let's look at this one. Okay. I just want to show you this one. Okay, so suppose I give you this and I tell you to factor it. Okay. Find all the zeros. Okay. The only thing to do to start, I mean, you might consider going at the rational zero theorem. The thing is, you can write down the rational zeros, and there will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 of them. Okay? And the thing is, if you can check all 18 of them, and none of them are going to work. Okay? Think about this for a second. This is degree 4, right? So we know it's got a positive leading coefficient, so we know it starts high and it ends high. It might or might not cross the x-axis. Okay, what are, let's see, we can find our y-intercept is 36. So, you know, it's possible. And I mean, honestly, if I were going to start this, I would sit there and I'd write down all, 18 of those factors, and I would try it. But I can tell you I've tried them all. Okay, they don't work. Okay, so yes, you very well might go through it. That'd be okay. But don't freak if nothing works. Don't assume that that means you did something wrong. This thing is even degree. It opens up. It is totally possible that it doesn't touch the x-axis. Okay, so if we did the rational zero theorem and it didn't work for us, then I would go back and think, is there anything else I can do? You know, can I factor this thing in any way? And do you remember doing the ones where it's quadratic type? Okay, if this were u squared plus 13u plus 36, we'd be real cool with u plus 9, u plus 4. Okay. Use the same idea over here with f. Say this is x squared plus 9, x squared plus 4. See that? Okay. So now can you see where the zeros are going to go? If you've got, those are both sums of squares, so we can't factor those any further. If we set the baby factors equal to 0, this one gives me x squared equals 9, negative 9. So x equals plus or minus 3i. This one gives me x squared equals negative 4, square root, x equals plus or minus 2i. So it's degree 4. I'm looking for 4 zeros. One of them is positive 3i. The other one's negative 3i. Positive 2i and negative 2i. Okay, so again, I wanted to show you this one because it does come up sometimes that, you know, perhaps the method you try first doesn't work. That's okay. Then try something else. If they give you these, you know, try different methods, because by the time we get to this section, we're after anything we've done in the course that'll work to get this thing factored. Okay. And let's do one more. Okay, so here's a third degree. Find the complex zero, write it in factored form. Okay, so again, I don't see anything I can do that would work easily on this, so I'm going to start with my rational zero theorem, and I'm going to do it way up high so that I've got lots of space. So I need the factors of 85. So plus or minus 1, 1 and 85, and then 5 and 17. Okay, I think those are all the factors of 85. Q is 1, so yay, plus or minus 1. So my possible rational zeros, plus or minus 1, 5, 17, or 85. Okay, so now again, remember what we do. If it's going to have a possible rational zero, it's going to be in that list. And if we can find a rational zero, then hopefully we can handle it from there, because that'll break this thing into a quadratic and we can deal with quadratics. Okay, so you just start with 1, 13, 57, 85. Bring down the 1. 1 times 1 is 1. 13 and 1 is 14. Well, that's not going to work. Try negative 1. Okay, and now again, I'm going to let you try. Okay, try negative 1, 5. I mean, you can do them in whatever order you want. I can tell you that 1, negative 1, and 5 don't work. First one I got to work was negative 5. Into 1, 13, 57, 85. And again, you just check them. You know, you're looking for a remainder of 0, so you just check them. Right? So negative 5 times 1 is negative 5. 13 minus 5 is 8. Negative 5 times 8 is negative 40. 57 minus 40 is 17. Negative 5 times 17 is negative 85. That's 0 as a remainder. Okay? So now we're lucky here because, again, this was cubic. So the minute I find out that x plus 5 goes into this, I know my quotient's quadratic. So I don't have to continue. I mean, negative 5 might work again. It might have a higher multiplicity than 1. But I don't have to keep doing this by synthetic division to find out. Okay, so right this minute, I've got x plus 5 times the quotient x squared plus 8x plus 17. Okay. Now, again, that quadratic factor completes the square quadratic formula. I'm not thinking much I can do with 17 is going to work here, so I'm going to go after quadratic formula on the quadratic. So negative 8 plus or minus the square root of b squared minus 4 times a times c all over 2a. So negative 8 plus or minus 64 minus 4 times 17 is negative 4. So negative 8 plus or minus 2i all over 2, which reduces for us to what? Negative 4 plus or minus I. Okay, so it was degree 3. I'm supposed to find all the zeros. So negative 5 is a 0. Negative 4 plus I is a 0. Negative 4 minus I is a 0. This is as factored as it gets. Okay. Hope this was helpful.